All right. So let me begin by thanking the organizers and also thanking in particular various people I have been in email contact with related. Oh, okay. It's not yet very important. Okay. So just warming up. So should I use this thing? Yeah. Is this on? No. This one. All right. Is it better? I can. I'll move this up a little. Hello. Right. The support staff. I would like to thank them for their kindness and patience and incredible efficiency and so on. All right. So my talk will be about de Sitter holography. Higher spin de Sitter holography, and this is about work that has been in progress for quite a long time now, together mostly, or just at least most recently with Dio Aninus, Ruben Monton, my student, and Zimo's son, my other student. And so, in the past couple of years, we've been slowly gathering what we believe to be important pieces of this puzzle. I don't think we're completely there yet, so I won't be able today to present you a microscopic computation of the de Sitter entropy, although I think I start actually to believe that this might well be within reach. All right, so let me start by motivation. And I'll try to be fast because I have too many slides. Well, perhaps I can summarize the motivation, by these two quotes. First one is from 100 years ago by Eddington, where he sort of just figured out that there is something like a Planck length, and says, in recent years, great progress has been made in knowledge of the excessively minute, but until we can appreciate details of structure down to the quadrillionth of a centimeter, i.e. the Planck length, the most sublime of all the forces of nature remains outside the purview of the theories of physics. So this quote here could be straight from any PhD thesis related to quantum gravity in the entire century coming afterwards. One thing that has progressed, though, is we have pocket calculators now, and so we actually do manage to compute the correct value of the Planck length given G, C, and H bar. But apart from that, well, as is clear from this quote, at least for gravity in the universe in which we live, the situation is, pretty much unchanged. So this is from lecture notes by Tom Hartman, where in his typical Tom Hartman dry tone points out, so these are lectures on ADS, CFT, black holes, quantum gravity, these things. Well, we will not say much more about the Sitter space in this course. A big reason for this is that we do not have any UV-complete theory of gravity in the Sitter like we do in anti-de Sitter. We also have no clear answer to the question, what is the de Sitter entropy? And since we live in the Sitter, this seems like a very important question, to say the least. Okay, so now I'll try to explain also why it's a difficult question. But so this is basically the situation in string theory. So we, in relation to the Sitter space in particular, right? So I guess sort of the fundamental core problem is that there are no classical de Sitter vacuum solutions in string theory. So the general no-go theorem that forbids this, and so therefore, well, any construction requires quantum effects due to the non-trivial topology of the internal manifold, as was pointed out by Katrukalis, Linde, and Trivedi. So once you allow these ingredients, actually it does turn out that there is a huge number of apparent de Sitter vacua, metastable de Sitter vacua you can construct in string theory, and this leads to the string theory landscape. Okay. But so this is all, plausible and good and well, but then, what do you, well, once you want to really do something with this and make firm predictions, you kind of hit what you could call the Great Wall of string theory. So the basic problem is, well, since there's no classical de Sitter solutions, it means there is basically no semi-classical control, which is in essence a manifestation of the Dine-Seiberg problem, which was pointed out in the 80s by Dine and Seiberg. So, well, that's problematic because if you do not have such, a complete theory, you basically, have no predictions, right? Like, for example, in a paper I wrote with Mike Douglas about 10 years ago, we computed in flux vacua under fairly generic assumptions the distribution of numbers of vacua with supersymmetry breaking scale f. This was f times supersymmetry breaking in flux vacua. And we found a distribution which universally for any flux compactification of type 2b string theory or F theory goes like this, f to the 5th df. So supersymmetry at low energies is suppressed. But what does this mean, right? Did we have a prediction that LHC was not going to find supersymmetry? Well, no, because there was always the possibility that there was another corner of the landscape that we had not seen, or that there were other effects that were more important, or there were some selection rules. And so as long as you do not have a complete framework, complete theory, that will always be the outcome, unfortunately. So it doesn't mean that nothing can be done, obviously, but obviously one would like to do better. And well, in ADS, of course, we do know that there are non-perturbative formulations of quantum gravity formulated through the, as a field theory, dual field theory through the ADS CFT correspondence. So the obvious generalization of that would be something like a DS CFT correspondence. And so this was proposed maybe like 15 years ago by various people and refined in various ways. Now, for reasons that I'll explain as well, it's been hard to find concrete examples, although well, a very simple, very concrete example has been proposed a few years ago, and that will be the focus of sort of the main part of the research part of my talk. So in any case, the consensus of all this is that the Sitter space is difficult. Okay? It's troubling, in the words of Susskind and collaborators. All right. So now, in principle, the idea is simple: to get from ADS, where everything is successful and beautiful and works, to DS. Essentially, all you need to do is a double Wick rotation, if you want. So you continue the ADS length L to IL, and the Poincare radial coordinate Z to I eta, where eta becomes conformal time in the Sitter, in this sense, the ADS metric to the DS metric. All right. So the boundary now, instead of a spatial boundary, is a boundary at future infinity. And all right, apart from that, again, you can write down asymptotic solutions of field equations of motion going to future infinity that are of the familiar form, familiar from ADS. So that all continues nicely. Then you can quantize field theory in the Sitter space. Again, a convenient set of canonical coordinates are exactly given by this alpha and beta parametrizing asymptotic solutions. Turns out they form essentially a canonical pair. So you impose canonical commutation relations of this form. Now, to formulate what DS CFT should mean, one way of doing this, roughly speaking, is, well, you can define sort of delta function or Dirichlet-Neumann boundary states, if you want, where either alpha or beta is put equal to 0. And once you do that, you can define something like the CFT in terms of correlation functions or matrix elements between the vacuum, which you could think of as a Euclidean vacuum, and, for example, the Dirichlet or the Neumann boundary state. These are insertions of fields at various points. Well, fields of these canonical coordinates, if you want. And so you can check that in field theory these do behave like correlators of a CFT, so then it's natural to conjecture that there should exist some CFT that exactly computes these things. Right? And you can do this for either boundary condition in the Sitter space in general. Right? So in the Sitter, all modes are normalizable, so this allows picking either one of them and both behave like CFTs. All right. Now, a variant of this, but it's of course closely related, is to express this in terms of Hartle-Hawking wave functions. Right? So if you exponentiate this and you consider eigenstates of, for example, this alpha operator, right, which you produce by just a translation, right, of the Dirichlet state, then if you just basically use this correspondence over here, then you see that you get a relation between the Hartle-Hawking wave functional, which is defined to be this thing. Right? You can think of these amplitudes here as given by path integrals with sort of no boundary past boundary conditions. Anyway, so then you see that you get a relation between the Hartle-Hawking wave function of the universe and the partition function, essentially, of the CFT with sources alpha. Okay. All right. And you see, well, these two choices you have between Dirichlet and Neumann boundary conditions, you can think of very nicely in the wave function language, at least formally, as saying that these two are Fourier transforms of each other. These are just the same wave function, but expressed in different bases. All right. Now, the challenges for the CFT, though, is that this has to be a very unconventional, very non-unitary CFT, right, if there is one. So first of all, it's clear that since the two-point function computes the second derivative of the logarithm of psi according to this correspondence, which you sort of want to peak, presumably, at the origin, this thing has to be negative, and this implies that necessarily the CFT computing this wave function must have an inner product that is not positive definite. Okay. Moreover, the central charge, if you do this analytic continuation, you see you use just a formula from ADS CFT, then you see you get some i's over here. In particular, in 4 dimensions, you see that the central charge becomes negative. Scalar masses in general are given in ADS by this formula. In DS, this again are given by a similar formula, but continued by L to IL. Now, this implies that the sort of the usual abundance of large conformal dimension operators, like trace of some matrix operator to the nth power, some high power, right? Like these are operators that sort of naturally occur in CFTs we know and love. They have very high conformal dimension, but from this relation here, you see that these would necessarily be tachyonic in the Sitter. So you don't want that. And conversely, heavy particles in the Sitter should correspond to operators which have large, complex, almost large imaginary conformal dimensions. Okay. So all of this is, of course, not what we used to in unitary CFTs. Of course, it is not at all inconsistent. Since the boundary here has no time, we don't want to use it as a CFT that has time evolution and all that. So that's all good. In a sense, you can view all of these things as some sort of CFT analog of the no-go theorems for classical the Sitter brain, for constructions of the Sitter, and so on. All right. So it has been hard in view of all this to generate examples. Of course, you could fantasize that perhaps there could be some bootstrap program that sort of produces all of these possible vacua in the string landscape. So it's nice to fantasize about that, of course, but it's not even clear at this point what should replace the unitarity constraint, which, if you want, is an additional motivation for this work. Okay, so then there are a number of objections raised by various people related to sort of general conceptual problems that arise when you assume the Sitter exists eternally. So these are valid points, but it doesn't mean, I believe, that there could not be sort of approximate, well, okay, just as the fact that I'm in a room now doesn't mean I cannot try to formulate theories of physics in terms of like scattering matrices that go infinitely far, and so on. But these are valid things to keep in mind and point to sort of constrain further the space of possibilities. All right. So now, basically, finally, the crucial, I think, issue that arises in the context of DCFT, which is very different from ADS-CFT, is, of course, that time is now emergent. Okay? And this means that the bulk Hilbert space is not equal to the conformal field theory state space. Okay? And the bulk Hamiltonian is not the CFT Hamiltonian. Right? Somewhat related to this, well, there are these like two CFTs, in fact, probably infinitely many CFTs if you vary boundary conditions for all the fields. So now, in general, you might want to compute correlators sort of mixing these operators. Right? Now, how should you do that? Should you sort of imagine like one big QFT that computes them all? Well, this runs into some problem which we'll call the commutator problem, and that is that so since we need to reproduce here, oops, where is it? Right. Well, this is the fundamental commutation relation of quantum mechanics. If you want these things to be both sort of part of some CFT, well, then you run into immediate trouble because, you see, then somehow this putative QFT correlator alpha beta would have to be equal to minus beta alpha. Right? Well, this should maybe be an I over 2 or something like that, which, if you think of these things as being computed by some Euclidean path integral, is clearly, I don't know, it's absolutely not what you expect in a Euclidean QFT. Right? And, well, again, related, supposedly, this CFT gives the wave function of the universe. However, that's literally only half or maybe like 1% of the story, because if you want to compute probabilities or vacuum-vacuum correlators and so on, you would have to integrate over phi. Okay, now once you start integrating over phi, which you have to do, then the question becomes, well, okay, so what measure do you use? Or in other words, what is really the phase space? Or more specifically, this is a wave function, but a wave function of what? Right. And again, also because the CFT does not contain the bulk Hamiltonian, it's also not clear how bulk dynamics emerges from all that. And so there's a number of research programs that are trying to investigate how one could do this. But let me not dwell on this. All right, now in view of time, let me skip over this slide. This was just an aside. If these pictures tickle your fancy, you can look at the slides online and then go to the relevant papers. It's just a side remark on this problem, but it's outside of the main line of this talk, so let me just move on. All right. So the goal of this work is we want to find an exact and complete model for de Sitter holography. Right? Now, I should emphasize, of course, interesting and very useful things can be said at some approximate level by analytic continuations from ADS-CFT, perturbation theory, and so on. There's lots of works in that direction. You can apply this to try to say something about early universe inflation, in strong coupling, and so on. This is not what we want to do. What we want is a model that is non-perturbative, complete, and does not require any, approximations or anything. Okay. Of course, there will be a price to pay, and the price to pay is that we will drop any requirement of resemblance with our own universe as long as we have a model that is a complete and consistent theory. All right. So what is this theory? Well, the model we will look at was proposed by Aninus, Hartmann, and Strominger, inspired by the higher spin gravity vector UN model correspondence in ADS. And they know that if you just make the scalars of the UN or Rho model ghost-like, make them fermionic instead of bosonic, then you get a theory that satisfies all of these requirements that I gave earlier. Okay. And so it's an incredibly simple theory because in one version, in the scalar Neumann version of the problem, it's just a free theory. Okay. So the VAs are the scalars. Then, for example, there is a single trace scalar primary, which is just this contraction. It has conformal dimension delta equals 1. And then there's a tower of higher spin for all the primaries. These correspond to higher spin particles of all spin S. Right. Now, this model gets around of many of these difficulties I mentioned. So the mass grad is positive, central charge is minus n as it should, the two-point function is negative as it should for a wave function in perturbation theory, and so on. Okay. And this means, since it's a free theory, that this partition function of the CFT is just a functional determinant given by this, so we get a very simple correspondence in principle between the Hartle-Hawking wave function of the Vasiliev universe and a functional determinant. All right. So first thing we did is sort of explore some mini superspace, version of this wave function, see how it behaves, and what we found is that, it's not important what the details are here, but for many sort of the infinite deformations you want to consider, in fact, for virtually all of them, it has this strongly damped behavior if you go in these particular directions. There's one exception, that's sort of the simplest one you can consider, which is the constant mode on the sphere, which turns out to be exponentially divergent. This is the logarithm of the wave function in terms of the deformation parameter, and this means there's an exponential divergence. These peaks down are zeros of the wave function, which are also perhaps somewhat peculiar. All right. So other studies have found similarly strange phenomena. Of course, you can take it any way you want. You can say, well, okay, there's another one model that just doesn't work. You can, just give up, or you can take it as a challenge. All right. Or, you can see anything you want in there. Now, okay, the point though is that you really cannot draw any conclusions whatsoever because of this main problem that really has not been resolved yet, and that is sort of what is this really supposed to be a wave function of, right? Of course, it's very important that you specify the correct domain and measure and so on of your wave function before drawing any conclusions, because as a simple example, right, e to the minus r over r diverges on the line, but it converges on the plane, for example, right? And there's issues of gauge invariance, which might lead to divergences. There's other redundancies. After all, this is a holographic theory, and this wave function with its localized coordinates doesn't seem particularly holographic, right? So, okay, so what could be the correct domain for this wave function? So the most general deformation you can consider is in terms of this bilocal field. So this is the most general free fields action you can write down. And now, as you notice here, of course, there's an enormous mismatch in this case between the source degrees of freedom and the sort of vector degrees of freedom, right? And, this can, of course, easily lead to all kinds of divergences, as a toy model illustrates, right? So say you have some matrix model, rectangular matrix model, for simplicity, just some Gaussian one, and let's say we have a wave function that's defined in this way, so B is sort of the analog of our bilocal source. I guess it should be a minus here. So then this is the wave function. Now you want to compute the norm squared of this wave function integrated over these Hermitian matrices B. And then a simple scaling argument shows you that this wave function is normalizable if and only if the number of source degrees of freedom does not exceed the number of field degrees of freedom, right? So the number of Bxy degrees of freedom should not be more than the number of Vxa degrees of freedom, right? Another way of seeing this is simply, if you just keep it integrated form and then integrate out B first as a Lagrange multiplier, if you have too many sources, you get too many delta function constraints from integrating out the B's here, so you get redundant constraints, so you get divergences. All right, so this makes very clear that just pretending like these general sources are actually, a physically correct thing to work with is completely misguided, right? Right, so this, applying this to our model, right? Like we have, no matter how you count, even if you take into account all possible, gauge fixings and so on, you find that the space of sources, in any way you might want to interpret this, is just way too large to match their canonically conjugate field variables or operators in the CFT. Okay, so no wonder this leads to pathologies. It's just not the correct parametrization. Okay, so the question is then, can we do better? Maybe we should parameterize the sources as bilinears. But this tends to run into this commutator problem I mentioned earlier. Now, another idea is to use so-called, what we call Berezin coherent states, which give us some sort of a consistent way of integrating over sources. So this is a general construction pointed out by Barin in the 70s that you can do for quantized UN models. And it's a map between sort of the standard quantization of vector models on the one hand, and on the other hand, sort of a dual phase space of sources. Okay, and so it reformulates basically this quantum mechanics into a geometric quantization or a Kähler quantization of this dual phase space of sources. It's completely equivalent to that. So it introduces coherent states to do that. Again, let me just skip over it because otherwise I won't have time. If you want to look at the details, you can look at the slides online. Right, so this defines the completely, there's a uniquely defined phase space that is constructed here. That phase space, even though it has these sort of source-like variables that at first sight look like it's way more degrees of freedom than these fermionic vectors, in fact, it does give the correct quantum mechanics because it's a compact phase space and it leads to a finite dimensional Hilbert space, etc. All right. So this construction really does seem to have the same sort of form of like what we want our wave function to be a function of, only it does lead to convergent integrals and a sensible notion of integration. It seems to correctly capture the degrees of freedom of the underlying theory, so that looks like this is the thing we need to use. All right, so, well, my time seems to be up. Let me point out, though, that we cannot directly use this story because the CFT state space is, well, unconventional, right? It doesn't have a positive definite norm. This translates into a change of sign here. Let me see, right, so since I have 0 minutes left, right. Okay, well, this is the last thing I wanted to say. So in order to turn all of this into statements about bulk physics, right, you need some operator, some CFT to bulk operator map, a la Hamilton, Cabet, Lifshitz, and Low. This can be done fairly generally. We follow the approach of these people. The result is that this is sort of the most general expression for a bulk field in terms of like putative CFT operators. Now, again, let me go fast here, or I run into trouble. So this, although this looks nice, it runs in the usual commutator problem in these constructions. Now, again, this precludes us basically from getting a quantum mechanics in the bulk. Now, Lorentzian ADS CFT, you kind of inherit Lorentzian quantum mechanics in the bulk from the CFT, but in DSCFT, again, it's the same problem always, right? Like, you don't have time in the boundary, and all right. Now, let me just very quickly flash that it turns out that there seems to be a rather remarkable way out. It's related to the quasi-normal mode quantization of Strominger et al. It seems to work only in the static patch. Static patch seems to be able to recover some notion of quantum mechanics. It's not quite global quantum mechanics in the sitter. That perhaps doesn't exist. It's sort of a half quantum mechanics that behaves and acts like quantum mechanics. It inherits this from the sort of quantum mechanics-like structure of this non-unitary CFT, reproducing, as I said already, this Strominger's quasi-normal mode quantization. I knew ahead of time I was going to run out of time, which I did. And, well, OK, so basically, pieces of the puzzle, I think they are converging. We're putting them together. And thank you very much.
Thank you. Questions?
Hi. So about this divergence, so at least naively, it seems like since the wave function is in zero mode is diverging exponentially in n, whereas at least naively, yeah, we may not know the integration for the measure, but naively it should be order n to the 0. But then nonetheless, you think maybe it'll cut off the divergence? So how does that
Yeah, yeah. Well, I mean, you see n doesn't, for example, just to give you an example, right? Like sort of okay. In fact, these Beijing coherent states do give a good example of a setup where using the proper integration measure turns horrible divergences into smooth convergences. So you see here, in particular, oops, right, like this formula over here, right, which is the decomposition of unity in terms of these states. So as you can see, right. So if you use some naive integration measure, you wouldn't have this entire factor. Now this S here corresponds to the number of spatial degrees of freedom, if you want. So if you think of this theory as living on a sphere, right? So it's sort of like, it's like the same sphere as in a Lorentzian CFT, like sort of the phase space of the theory would live on, right? The spatial sphere it's a two-sphere in a three-dimensional case, okay? So S is a number of so S goes to infinity in the continuum limit, and so you see that that plays an extremely important role. That in fact, as soon as S gets larger than N, right, completely overpowers this and makes N in fact completely irrelevant. All right, so it's very conceivable that this constant mode is something like an you can maybe think of it as like the radial. Say you integrate over a very large dimensional sphere. Right? Constant mode somehow corresponds to the radial direction, and then the sort of orthogonal modes correspond to the angular directions. Okay, those gave like finite, like damped results. Sorry.
We need n orthogonal directions with something that's diverging like some exponential.
Well, there's way more than n, right? Like there's like in the continuum limit, there's like n is completely, naively at least, n becomes completely irrelevant in the continuum limit as far as convergence is concerned, right? So I see your argument, right? But so in this setup over here, right? If you embedded this, you could easily just use this measure and then embed these wave functions in there. The kind of divergence we found, would be completely irrelevant, because eventually it's this power, this S, that really dominates the whole thing, and it's only for questions pertaining to a subset of degrees of freedom that is sort of less than n somehow, that n really plays any role. I mean, at least for normalization.
I think we should move on.
Yeah.
Let's thank Frederik again.